change gears a little bit. After a long time, a long day full of electronic structure calculations and quantum chemical calculations, we are switching now to methods to measure something of the electronic structure. And the experimental methods which we are using for detecting or learning something about electrons at transition metal complexes are, sorry, I'm looking for my pointer now, here, are electron paramagnetic resonance, the spectroscopy, magnetic susceptibility measurement, Mössbauer spectroscopy with applied fields when it comes to the topics which we are talking about now, and magnetic circular dichroism. These three methods are ground state methods. We are usually only detecting or learning something about the electronic ground state of a transition metal complex, whereas MCD spectroscopy connects the two worlds, ground state and excited state. And we need a theory which describes the electronic structure and parameterizes the experimental results under a common clamp. And this theory is Spin Hamiltonian Formalism. It's a sort of a sub-theory which is related or can be derived from Ligand field theory or other higher methods, but it's used, as I said, to parameterize experimental data and to yield parameters which we can also derive or obtain from higher and real theoretical calculations. What do we have to explain for these methods? When it comes to EPR spectroscopy, we can imagine a spin a half in a magnetic field has spin up and spin down orientations. The energy of these up and down states depends on the strength of the applied field. We change the field and shine a certain light, radiation of a fixed frequency on the sample, and then we can make a transition between these levels. We can make a magnetic resonance, and that is what we have to explain by a certain theory, at which fields we get the resonances and what will be the transition probabilities. So that is what we have, that we can calculate. When it comes to magnetochemistry, so magnetic measurements of paramagnetic samples, that is a topic Professor Glaser will talk about in detail, but what we will have to explain at the end is the magnetization of a sample. So we put a sample into a magnetic field, this sample will distort the field, this distortion can be detected and can be converted into voltage, into a signal which is proportional to the magnetization, and we can follow this magnetization as a function of a temperature and applied field. Again, something which we have to explain by this Spin Hamiltonian theory. And in iron 57 Mössbauer spectroscopy, sorry, I have to adjust the microphone. Iron 57 Mössbauer spectroscopy, with applied fields, we will have a nucleus which is the reporter of our system, and that nucleus will feel a field which comes from the magnetic moment of the electrons in the open shells of iron in corresponding states, oxidation states. So all these methods are ground state methods, and we have to describe this magnetic behavior of these systems in terms of such a Spin Hamiltonian theory. In order to imagine what is the job, what is the task, I have here some comparison of energies. In an EPR experiment, in the typical so-called expert EPR experiment, we have radiation with a microwave quantum of about 0.3 wave numbers. Very small compared to the energies which you can calculate. Another thing, another number, rule of thumb. 1.55 Tesla times mu Bohr corresponds to a thermal energy of 1 Kelvin. Pretty small. So magnetic Zeeman interaction is a weak interaction. When it comes to hyperfine interactions, or the connection between the nucleus and the electrons, the nuclear and the electron spin, these hyperfine coupling constants are of the order of 10 to the minus 3 wave numbers. Whereas optical transitions are of the order 10 to 3 to 10 to 5 or 10 to 4 wave numbers. So that is the framework within which we have to explain our data. And when we look at ground states, on the basis of what we have learned yesterday already, we think in terms of Ligand field splitting. We have Ligand field splitting of electronic terms. And then and this Ligand field splitting leads to quench of the orbital momentum of these states. You heard that yesterday already. But when we switch on in the Gedanken experiment, the spin-orbit coupling tends to mix excited state into the ground state, and that allows the electron again to form a ring current, to go around the atom, so to have a magnetic orbital momentum. So the electron can go around, and we have a field, so to say, which is seen, for instance, by our Mössbauer nucleus, and which adds to the externally applied field, and what we have at the end is the magnetic behavior which cannot be described anymore by an electronic G factor of the Zeeman interaction, which is 2.0, but it's changed, it will be anisotropic, and we will have, in addition, zero field splitting. So that is the range where that is the task, that is the job, and the thing which we have to describe. We have to describe this magnetic behavior, which is related, or which depends on Ligand field splitting and spin-orbit coupling at the end. So, and we want to parameterize these effects which we see here in the ground state. We want to parameterize in a convenient way and in a sufficiently accurate and correct way without using the full gear or full theory. We don't need to know the full range of excited states. We have to describe the ground state properties. And that is the job of this Spin Hamiltonian Formalism. We can look at this again in this type of picture. So we have here the effect on an energy scale, the effect of electrostatic or Coulomb interaction of electrons with the nuclei and with themselves. The electronic repulsion generates, let's say, for the atom, it will generate these terms. And with the Ligand field, we get additional splitting, and we get this quench of the orbital momentum, and that is now the example for the iron 3 high spin, for instance, of a manganese 2, a 3d5 configuration. The ground state would be a 6s state, and under the influence of the spin-orbit coupling, this degenerate ground state, this six-fold spin degenerate ground state, will split into so-called Kramer's states. So we'll have a zero field splitting, and under the influence of a magnetic field, these levels have, in addition, Zeeman splitting, and watch here the breaking of these lines. So this is 10,000 wave numbers, this is of the order of 1 wave number or so, or 10 wave numbers, and that is what we have to describe by the Spin Hamiltonian Formalism. Yeah, okay, that's the job we have to do. And the Spin Hamiltonian Formalism is, or was from the beginning, a very formal procedure. It was assumed that there is a set of n levels, which is fairly nicely isolated from excited state, or even levels which are below that. So a set of levels which is close together with a multiplicity n. And then we introduce a fictitious spin formally, which is selected such that its multiplicity matches the number of states which we have to describe. That is mostly a physical spin, but not always. I will show you in a few minutes an example where it is not a physical spin. And then we have to find an operator, we have to find a Hamilton operator, which describes the energies and the properties of this system. And if possible, this operator should have only spin components, because we're only interested in magnetic properties. And this operator is then the so-called Spin Hamiltonian. And historically, this Spin Hamiltonian was introduced by using the crystal field potential, or the symmetry elements of the crystal field potential, so the electrostatic potential, that can be described in spherical harmonics, let's say, and one can find operators for this electrostatic potential, but there is a possibility to convert such operators by using an operator equivalence into angular momentum operators. So such operators, such Hamiltonian operators, O, which depend on some potentials of s squared, s to the fourth, and so on, and with some coefficients here. And up to the order 2, one has this relation here. It's not very important that you remember that now. I just want to say one can describe this things in terms of spin operators. And then one would have, that would lead to a zero-field splitting, as I will demonstrate in a few minutes, and that would have then parameters E and E, for instance, or that is a convention which is introduced very often. That would be a very bad approach for us, because that would provide no real or realistic connection between our electronic structure theory and these spin Hamiltonian parameters. But luckily, it is possible to derive the same type of spin Hamiltonian from a perturbation treatment of spin-orbit coupling in ligand field theory. And I will not go deeper into this topic. That is also quite complex and would certainly lead astray here in this case, but there is a nice book article, for instance, recently where this is described. And I want to direct your interest also to these special interest lectures. So there will be a special interest lecture by Frank Wiese about effective Hamiltonians. I guess that this will also touch the spin Hamiltonian. There will be advanced ligand field theory by Michael Atanasov. I guess that you also will introduce ligand spin Hamiltonian, so make the connection between ligand field theory and spin Hamiltonian. And Dimitri Manganas will talk about theoretical spectroscopy beyond DFT that will also touch this topic. So now we will go a little bit deeper into the spin Hamiltonian and learn a little bit about the properties and how to deal with such a thing. I think for many chemists this is quite a frightening expression, and we should learn how to handle this thing a little bit. That's my goal here. So we have here, let's say, 3 different terms in this Hamiltonian. One is depending on a parameter D, one is depending on a parameter E, or for by convention, very often it is written as E over D, so you see this bracket around this one here. And there is a Zeeman term, for sure, because we want to describe magnetic properties. And there can be many, many more terms. So this would be a spin Hamiltonian for a single metal ion, a single transition metal ion. We can have several transition metal ions. We would have more of this type of spin Hamiltonian. We would have interaction Hamiltonian to describe the exchange interaction between these transition metal sides. That will be the main topic, or which one of the main topics of magnetochemistry of the next talk. Or there can be interaction with the nucleus, so we're going to have hyperfine interaction and so on. But today I will focus simply on this single ion spin Hamiltonian. One can say that the ligand field parameters, which are quite telling to chemists, which have chemical information, they are condensed, so to say, into these spin Hamiltonian parameters D and E over D and the G matrix. And that is very nice, because that is common to all, or this formalism is very nice because it will be common to all the experimental methods which I presented, and it will also provide a connection to the theory. So that is a very nice place to rest, as Griffith Butts coined it. Okay, before we go deeper into more formalism, just a note that sometimes you can see the spin Hamiltonian written in this form. Zeeman term is the same, but the zero-field splitting terms are different, so it's written SDS, so it's bilinear, and then the D is a D tensor, and one can make a connection between the components of the D tensor and these D and E values if one assumes that this D tensor is traceless. So that is a boundary condition, which is not physically true, but for a single ion it doesn't matter because it only shifts the total energy of the system. So we may readjust the energy zero. And then one can convert this into each other. And another note about the energies of these systems for transition metal complexes. The zero-field splitting is usually larger than the Zeeman interaction that we can generate by applying fields of 1 to 10 Tesla or so. That is not true for other ions. So, what do we do with this spin Hamiltonian? So we have a Hamilton operator. We need a basis function where this can operate on. And this is the most easiest, and that is the beauty of this spin Hamiltonian, because that it is so simple, because we can use basis functions. We will have a closed set of basis functions. We have a number of states n, so we need n basis functions. And these basis functions are the usual SM basis functions that you all know. And the nice thing is, so we will have quantum numbers m from minus s to s, and we will use this bracket notation, this notation for this basis function in the future. So we have to diagonalize this spin Hamiltonian, and the result will be that the final functions after the diagonalization, so we have all the interaction included, they are probably not along the same axis, they have different strengths and so on, that will lead then, after the diagonalization, to a linear combination of such angular momentum, of such spin functions. And with some coefficients in front of them. And that will be the goal, to find these wave functions and to find the energy of this state. So we can set up this Hamilton, or we can set up now the Hamilton matrix of this operator by using these basis functions. And that is a relatively easy job again, because we can use the normal rules of angular momentum operator. What happens if an SZ operator operates on such a wave function? Very simple. It yields the same wave function and the quantum number m. No? This SZ operates on this wave function. It yields the same wave function and the quantum number m. So very slow today, my explanation. SZ square operating on this function yields again the same wave function and the multiplicity of the spin, s times s plus 1. Okay? In directions which are not the x, which are not the z direction, which is usually the quantization axis of the Zeeman effect and so on. So if you have x and y components for this spin, it gets a little bit more complicated, because we have to introduce these so-called ladder operators. These are operators which change the wave function. So the Sx operator is written as the sum of these two operators, and the Sy operator is imaginary, so it has a minus I in front, and this difference of these two operators. And what are these two operators doing? That is written here. When this S plus or this S minus operator are operating on M, so this is now a short notation, sorry, that was didactically not very good. So this is a short notation for the same wave function. So operating on this one, it yields the wave function with M increased by 1 or shifted down by 1. Therefore, these latter operators. And in front of this, we have this coefficient, it's S times S plus 1 minus M times M plus or minus 1, depending on what operator it was. And these are the only rules which we have to know, this one, and let's say this one, and then we can go on. The others are, let's say, convenient rewriting of these operators. Okay. For those which are really not experienced with angular momentum operators or operators at all, a few more notes. These operators are linear operators, so we can, when we have an operator to the square operating on a wave function, we can say it's operating twice. So the first one is operating on the wave function, the other one is out of the bracket. We get a new wave function and a coefficient, and then this one is shifted through, it's operating on the wave function, and we get a third wave function in general with another coefficient. And such a matrix element, when this, for instance, when this is a number, we can pull out numbers out of this business, and then we have, for instance, such a matrix element, and these wave functions are orthonormal, so they yield the matrix element yields a 1, and what we gain is the number in this case. Okay, this is just a glimpse into how to deal with this relatively simple thing. So now we can get these matrix elements where we have the wave function on the left and on the right and the operator in between. Okay, but before we do this, we look at a very simple example which we can do without diagonalization. So let's assume we have an iron 3 high spin, as I had before. Let's assume we have no rhombicity parameters, so the E is 0, the E over D is 0, and the field is 0. Then the spin Hamiltonian out of the sum, which I had written down here, is relatively simple. What is left over is only the term with the D in front. So D times SZ to the square, minus an energy balancing term. So that is only shifting the energy, as we will see in a moment. Because we do not have to diagonalize, because we know that the SZ operator, other way around, we know that the normal basis functions, Sm, are eigenfunctions of this SZ operator. The SZ operator yields the same function. And when we operate it twice, it yields twice the same function, with something in front, namely the M. So we apply this twice on, on such an Sm function. Know what I mean? Christian, is that clear? This microphone is very loud. Yeah. So if we have such an SZ operator to the square on such a function, it means we have to operate it once. No? What is the result of this one? It yields the M times the same function. And now this is again operated by this one, and then we get m to the square. Okay, and the second part here with this number here, when we put in 5/2 times 7/2 divided by 3, that yields 35/12. So we can write the energies, the eigenstate, the eigenvalues of this simple operator, we can write very easily without using any diagonalization. What we have is then an equation which tells us that the energy of the states depends on the magnetic quantum number to the square. That means we will get a splitting of levels, we will get no splitting of levels plus minus 1/2, plus minus 3/2, plus minus 5/2, but we get a splitting between these doublets. We get a splitting into so-called Kramer's doublets. And the reason that this has to go into such doublets is a deep principle of symmetry in nature. It has to do with time reversal invariance, and Jan Henry Kramers discovered this thing and has derived this, which shows that for half-integer spin systems without applied magnetic field, they must remain degenerate always in doublets at least. These are these famous Kramer's doublets. So the S is not a genitive S, it's a part of the name. Okay, and from that one we can go on, or no, one step back first. So I said that this zero-field splitting for transition metal complexes is usually larger than the Zeeman splitting that we can induce by applying a magnetic field. And then it turns out that life can be even more simplified than what I started to explain now. Namely, when it comes to EPR spectroscopy, one can say, okay, if this splitting is very small under the influence of a magnetic field, and this splitting is very small under the influence of a magnetic field, and same for this one, we can describe each of these Kramer's doublet with an effective spin Hamiltonian, because that fulfills the condition for a spin Hamiltonian. We have a set of two levels, which is energetically well isolated from excited states or other states. Let's describe this by another effective spin Hamiltonian. And the nice thing is, when we have a doublet, the spin Hamiltonian is very simple, because we need only a spin of 1/2, and for a spin of 1/2, one can show, or you can easily convince yourself, that there is no zero-field splitting, because zero-field splitting needs only splitting into doublets, so we have already a doublet, so we need only a Zeeman term for the spin Hamiltonian. So that is now an example where we have a spin Hamiltonian with a fictitious or an effective spin which is not physical. Then we have 3 spin Hamiltonians for each of these Kramer's doublets, and each of these spin Hamiltonians has a so-called effective G matrix. These are now the famous effective G values in EPR spectroscopy. And that is the way how we parameterize these EPR spectra usually. And we can get these effective G values if we solve this this spin Hamiltonian, relatively simple. We can spin 1/2, that yields again this S operator for the different direction, x, y, and z. So if we take the field in z direction, for instance, we get the normal Zeeman, the Zeeman term that the splitting is effective G value times mu times the field. And that defines us the effective G value for this field direction. And what we observe in this effective spin Hamiltonian for Kramer's doublets is the following. When we apply a magnetic field in the z direction, we get a splitting as we expected, no? Because this SZ operator in this case, for this are the usual spin function, Sm are the eigenfunctions, and we get splitting according to a G value of 2. But for the next one, we get a splitting which is much larger, so this separation of levels as a function of field is much stronger, because physically it was the plus minus 3/2 Kramer's doublet with the multiplet spin of 5/2. No? That was the ms plus minus 3/2, and this was the plus minus 5/2. So we get splittings which are 3 times larger than the ground state and 5 times larger than the ground state. And now in this effective formulation, this effect is merged or is put into the effective G value. That means when we describe it with spin of 1/2, we have an effective G value of 2, effective G value of 6, and effective G value of 10. That makes these large effective G values that I sometimes read about in EPR literature. And then life becomes more complicated. I will not demonstrate that, how we get it. But if we apply now the field in the x or in the y direction, then we will have a large Zeeman splitting integron, Kramer's doublet, which formerly was labeled plus minus 1/2. This plus minus 1/2 cannot be true anymore now because the field is not along the z direction, but it's along the x or the y direction, so that will mix the wave functions, will generate different wave functions, but as a label, usually one keeps this, this term plus minus 1. So there's a large splitting in the lowest Kramer's doublet. There is for weak fields no splitting in the first excited Kramer's doublet, and there's no splitting in the second Kramer's doublet. So in the first case, we had G values, no, let's say for this Kramer's doublet, for this Kramer's doublet now, we have anisotropic G values. We have G values in the order of x, y, z. We have G values of 6, 6, and 2. And for the second Kramer's doublet, we have G values of 0, 0, 6. And here we have 0, 0, 10. And if one switches on the rhombicity, the picture changes dramatically. The picture does not depend, or the result does not depend on the D value, because we said the D value is very large and the Kramer's doublets are isolated. So whether these are a little bit closer or a little bit further apart, that will not change the picture. They're far apart anyhow. But the effective G value depends dramatically on the field direction now. The lowest Kramer's doublet, that has now, for the x direction, a small G value of less than 1. For the y direction, it's almost 10. And for the z direction, it's again very low. The same behavior we have in the highest Kramer's doublet, only in different directions. We have small, small, large. Here we have small, large, small. And finally, the middle Kramer's doublet, that does not depend on the direction of the applied field. That has always G values of 4.3. And that, by the way, is the reason why in EPR on iron complexes, we have always this shit iron peak at 4.3. Namely, if we have a little bit iron 3, which easily is rhombic, then this middle Kramer's doublet has all the spectral intensity at 1 G value. And therefore, this line peaks out of the spectrum. Okay, the effective G values depend on the rhombicity parameter in this case. And that can be drawn in 3 diagrams, so-called rhombogram. This is a rhombogram, or these 3 panels form the rhombogram for S equal 5/2. That is, for the lowest Kramer's doublet, you see we have this situation when the rhombicity is 0, that is what we had before. We had G values of 6, 6, these are X, Y, and Z. Oh, these are labeled here, the coding of these colors is there. So it's X, Y, and Z here. For the low square subnet, so 6, 6, and 2. Full rhombicity would be so it's the other way around. Large, small, small, and here the same on the highest grammar doublet. Or for small rhombicity we have 0, 0, 6, and for the highest grammar doublet 0, 0, 10. So this graph tells you what you should expect. I mean, it's calculated for the case that the electronic G value, so this is calculated with the full multiplet Hamiltonian, and then the values derived for the independent Kramer doublets. So these are the effective G values that one can expect in an EPR experiment in this situation. When the G value of the full spin was 2, then we have this effective G value. So that is now, if we find an EPR spectrum and find some resonances, we can search on this rhombicity scale and find out which G values match to the experiment. So that is a very good approach for a first interpretation of EPR spectra. And such an EPR spectrum, for instance, can look like this one. You will hear about EPR spectroscopy tomorrow in detail, but let's assume without understanding the spectrum, the shape of the spectrum in detail, we have, in such a case, we have 2 G values at SIG and 1 at 2, and that is very nice because this is a porphyrin with an iron 3 that has a 4-fold symmetry, that should have axial symmetry in the spin Hamiltonian, and therefore we have this nice axial EPR spectrum. Okay, I was wondering whether I should say something about the EPR spectra of the highest Kramer doublet or the middle Kramer doublet in this situation. Can you imagine if you have G values of 6 in one direction and 0 in the other direction, and we record a powder spectrum? We had the resonance condition briefly on the side. I mean, we will learn about this resonance condition more tomorrow, as I said. But if you imagine you make a powder measurement and you have a G value which is 0, where is the resonance field? At which resonance would you expect this field? No? That would be infinitively high. And that would be a spectrum which would be infinitively wide and therefore infinitively flat. And so these Kramer doublets with 0 rhombicity are not detectable. Okay, such rhombograms can be drawn also for other half-integer spin systems, no? Because only there they make sense, because we have this Kramer doublet without this degenerate doublet, without applied magnetic field, which are isolated from each other, and then we describe the Zeeman effect with this effective G value. So that is now for 3/2 the rhombogram. I can go into detail of that, and one can also find tabulated things of higher spins, 7/2, 9/2, 11/2, whatever one wants, one can calculate. Just a little trick probably at the side. If one has axial symmetry, one can show that the ±1/2 doublet, the G value, Gx and Gy, that should be always the same if the rhombicity is 0, then this tells us what is the spin of the system. The effective G value label is 2s + 1, one can show. That's a tiny little explanation. Okay, this is an example where the spin, let's say, is not known. That is, again, a synthetic porphyrin that was treated with MCPBA, with a peracid, to make a high-valent iron 5 complex, so to say. And what then is seen, this EPR spectrum has 2 G values, 2 around 4, pretty close together, not fully axial, but 1 at 2. And if we apply this rule, that the effective G value in the perpendicular direction is 4, if that is 2s + 1, then the spin must be 3/2. So that is a high spin iron 5, or an iron 4 radical actually it is, which has a spin of 3/2. So that was the result. Okay, now we should go a little bit deeper into what general spin Hamiltonian, and now we have to go into this diagonalization business. So this is the Hamiltonian we had before on the screen, and we will write it now for an example of S equals 3 half, in order to make it not too large, not too big, the Hamilton matrix. So we can treat these three different terms separately. The one which is depending on D is this D times SZ squared term, so we can call this HD. The term with the E over D, or with the E dependence, is this one. We can rewrite that by using this recipe which I gave before. We can rewrite that in the form that we have E half times S plus to the square plus S minus to the square. And for the Zeeman term, we have here a vector product with a G matrix in between. For the moment, we assume that this G matrix is diagonal in our XYZ coordinate system, and then we can rewrite this term by calculating the vector product with the G matrix in between. Then we get three elements depending on this Gx, Gy, Gz, and this capital G is now includes also the mu and the field component. So that is the way to start with this situation. And what we then have to fill out is at the end, okay, we have here, we need a little bit more treatment, as I told you already. The Sx operator can be written with S plus and S minus, and the Sy operator can be rewritten with S plus and S minus. And now it should be possible to fill out this Hamilton matrix. It should be possible to find out all these matrix elements between all n basis function numbers, and I use again this short notation for Sm in this way, and fill out that in a matrix form. I hope everybody is comfortable with this one. In this angular momentum operator business, an important question is always, where are the zeros in this matrix? So if you look, let's say, at this HD term, D times Sz squared, which part of this Hamilton matrix can have a contribution from that term? Can only be the diagonal element. Because we had that here, when the Sz operator is operating on such a wave function, whatever it does, it always is the same wave function. That means if we would have a matrix element let's say 3 half, something in between 5 half, whatever the result here is. When this is a number, we can pull it out, and then such a matrix element, because the basis functions are orthonormal, such a matrix element is 0. That means the first term is pretty simple. That can have contributions only on the diagonal. What will happen with this operator? If we have the S plus operator to the square, what is the result of this one? If we have S plus twice, and basis function n. So when we operate it once, for instance, if we have 1 half here, and we let S plus operate on 1 half, what is the result? 3 half, okay? Plus a coefficient in front. Then we pull out the coefficient, the S plus operates again, then we are at 5 half. So this S plus operator can only yield matrix elements which are off diagonal by 2. So that is the second subdiagonal, and nothing else. So the D elements at the end will be here on these places, and those which are off by 2 due to the S plus and the S minus operators, that is not here, but it's 2 off. So we have this one. And this one. Okay, that's already that one. And when we go now to the Zeeman interaction, the SZ term is again easy, because the SZ operator always yields the same M function, so that will be only diagonal elements. And the SX and the SY operators, because we can rewrite them with S plus and S minus operators, they will contribute only elements which are off by 1. So the first subdiagonal. So this Hamilton matrix, when it is a big spin, is pretty empty. It has only a band of elements around the diagonal. So and here it is summarized. The HD element yields only HD operator yields only diagonal elements. The rhombicity yields only second subdiagonal. The SZ operator diagonal elements, and the other one first subdiagonal. Very easy, very simple. And the second subdiagonal, yeah. Okay, these are these elements. Okay, we can easily calculate these elements. For instance, for the D operator, and that is what we did before already for the case where we had no field applied. We can do this calculation. So we have this part with the operator, and this part is a number. So we can split this matrix element or this operator in 2 matrix elements, if you like. So if we have M SZ square minus 5/4 or so, and the whole thing times D. We can split that in 2 matrix elements. We have the M SZ square M element minus the M over M element. This is easy because this is a number. We can put it out. We have the matrix element, which is then 1. And here we have the M to the square coming out, and the same matrix element M. And therefore, these expressions are pretty simple. So we will have to fill in matrix element of this type. For the GZ value and the Zeeman interaction along the Z axis, we have the SZ operator only once, so it yields the M quantum number only once. Okay. So when it comes to second to subdiagonal elements, it gets a little bit more complicated. We have to make use of this expression that I have shown before. And when we do the business, I think we do not do that now in the lecture room, but when we look at this Hamilton matrix, at the end we have this result. And we have at the diagonal the D values, plus D, minus D in this example. We have the rhombicity parameters we have here, and the diagonal or the GZ elements are here on the diagonal again, and for the field along the X or the Y axis, for the field components along the X or the Y axis, we have this element in the first subdiagonal. So and that is now the point where the whole thing goes into computer. We have to find the eigenvalues and the eigenfunctions by diagonalization of this system. The diagonalization means nothing else than shifting, adding and subtracting and multiplying rows and lines of this matrix, so that at the end we get wave functions, we get functions which are linear combinations of these basis functions, and we have nothing else than elements on the diagonal. Such a Hamilton matrix, when it is calculated with these numbers, may look like this one in these cases without a Zeeman interaction, and we then apply a field of 300 millitesla, which is a typical resonance field of an X-band EPR experiment, we get out now new wave functions, which are these linear combinations of the basis functions. And these can be complex. At least in general, these are complex. That means they have real and imaginary contributions. And for instance, for this first state, the wave function is this linear combination, so it has mainly contribution from -1/2 in the real part, but it has also an imaginary part of -1/2, which is quite substantial. Or in another case, we have here mainly contribution from the -3/2 in the wave function number 3. So that is, these are numbers at the end. These coefficients, that is something which we need, for instance, when we want to calculate EPR intensities. We need this composition of the diagonalized wave function. And what is the behavior of this spin 3/2 system with a zero-field splitting of 0.8 wave numbers? I selected that for no special reason, and a certain rhombicity parameter is 0.5, and a g-value of 2, we assume now for the moment. What we have here now, when we apply the field in the z direction, that is what we had before, but now I do not have this condition that the zero-field splitting is large. This is a general situation now. And now I was quite prudent, and I changed the field, it was not prudent, I changed the field to 1 Tesla. That is not a very big field. But the zero-field splitting is not so very high. No, I told you, in an EPR experiment, the microwave quantum is 0.3 wave numbers. So that would be an EPR experiment, such a situation where the Kramer's doublets are not really largely separated from each other. And what we see here, for weak applied fields along the z-axis, everything behaves quite normal. This has a splitting like G2, and this has a splitting like G3. So large splitting, small splitting. But when it comes to larger field, these two Kramer's doublets start to run into each other. And because this is now not an axial symmetry anymore, because we have a rhombicity parameter, these two doublets cannot cross. So they mix with each other, the wave function, the nature of this wave function changes, and the slope of these curves, so they repel each other, the slope of these curves went down, and they do not cross. So we have such an avoided crossing in this case. When the field is applied in x direction, the situation is even wilder. For small fields, we have nice linear splitting. For very small fields, we have nice linear splitting in this Kramer's doublet, but nothing in this one. That was the same behavior as we had in the rhombicity interrombogram before, and the same situation when the field is applied in the y direction. But when these fields are then a little bit larger, so from here on, there's no linear splitting anymore. They do not behave as independent doublets. They start to mix with each other, these wave functions, and therefore the energy of these states is not a linear function of the applied field anymore. And if you want to describe an EPR resonance in such a case, it matters whether there is this bending or not. And the second property that we can look at here in this case is the so-called spin expectation value. That the spin expectation value is this matrix element of the spin as an operator in between. So the spin expectation value written like this one, this is a vector, that is the matrix element of our wave function and the S operator. So that is what we expect, or that is something what we can measure. If we do, for instance, magnetic measurements, we can measure these spin expectation values, for instance. And the spin expectation values, you see in this situation, in the fields along the z-axis, they are as they should be, plus and minus 3/2, plus and minus 1/2, but later on they change dramatically, and when the field is not along this z-axis, the condensation axis of the zero-field splitting, then this angle between the field and the axis of the zero-field splitting, that mixes these wave functions, and we get quite a wild behavior. By the way, this is not real, this is a I was too lazy to track the nature of these wave functions. The colors should not change here at this step where we have some strange crossing here at this level. Okay, so we can summarize this behavior for small applied fields, and the symmetry direction is smaller than the zero field splitting, significantly smaller than the zero field splitting. For fields for the plus minus 1/2 grammar standard, fields along the z-axis give a spin expectation value of 1/2, and for fields along the x or the y-axis, we get a spin expectation value of 1. And this is called, so to say, an easy plane of magnetization. That means when we apply a field in an arbitrary direction, the component of the field along the z-axis will induce much less spin expectation value than the field components in the x and the y direction, and therefore the magnetization, the spin expectation value, tends to point into the xy direction or the xy plane. For the plus minus 3/2 doublet, it's the other way around. Fields parallel to z generate large spin expectation values, and in x and y there is no spin expectation value. So in this case, the magnetization tends to stick into the z direction. That is called an easy axis of magnetization. So now we come to the expectation values, the properties that we can calculate from this spin Hamiltonian. We have diagonalized it, we have the energies and the eigenfunctions, and now we can calculate magnetic moments. A magnetic moment is defined, a microscopic magnetic moment of a state is defined as the derivative of the energy of the state with respect to the applied field. So that would be the operator in this case. So that means the state is only magnetic when its energy depends on the field. And in detail you will hear that in the next lecture by Professor Glaser. So a molar magnetization in the sample, we never measured one single molecule, we measure a whole ensemble of molecules. So we need then something like the molar magnetization. And the molar magnetization depends in such a zero field split, not zero field, Zeeman split situation of a spin system. We apply the field, we make the magnetic splitting, and then we have a certain Boltzmann population of spin up and spin down, or in a more complex spin system, this up and down is also a little bit more complicated, but what we can do, we can derive these magnetic moments from the energy. We have to determine for every state the energy dependence on the field, so the slope of this eigenvalue as a function of the field. So for every state has a magnetic moment, and we have to sum up this magnetic moment and simply apply a Boltzmann weight. That will give us the magnetization of this case. Okay, more in the next lecture. And just a note, so we can do it with the energies, numerically, calculating, diagonalizing the spin Hamiltonian at 2 or 3 different fields, which have a finite difference, and we can form the difference difference quotient and determine the magnetic moment. Or we can make use of the Hellman-Feynman theorem, which tells us that the derivative of the energy as a function of the field can be replaced as the expectation value of the derived operator. So we take the derivation of the operator with the field, and only the Zeeman terms are left over, and that shows us, since this one has only Zeeman components, that shows us that this will dependent, or that the magnetic moment will depend on the spin expectation value. Sorry, that was complicated. So the magnetic moment is a function of the spin expectation value. Good. In the EPR experiment, what we have to calculate is clear. We have to calculate the energy splitting for a certain field or fields, and we have to search for the resonance, because in the EPR spectrometer we have a fixed frequency, so we have a certain quantum split, quantum energy. We have to find the field where this resonance happens. That is a certain demand, because one cannot do that brute force, or one should not do that brute force. One has to think a little bit about how to search this resonance field cleverly. And in general, for calculating a powder spectrum, that would mean one has to select a certain field direction first, then guess a field, diagonalize the spin Hamiltonian, and change it so until with the different fields until we have the resonance field. Then we have the energies, and so the energies, the resonance field, and the composition of the wave function. Then we can calculate transition probabilities with this wave function, and the operator for calculating the probabilities is the S operator perpendicular to the applied field, because in an EPR experiment we have the oscillating microwave field is perpendicular to the applied field. So we get this transition probability, and then go to the next direction and sum up all these results which we have here. That gives us the powder EPR spectrum. When it comes to hyperfine interaction, namely either in an EPR Endor experiment or in a Mössbauer IM57 Mössbauer spectrum, we have to add something to the spin Hamiltonian, because now we have to add the interaction of the nucleus with the field and the interaction between the nuclear spin and the electronic spin. So the nuclear spin, electronic spin, that is the so-called high-valent coupling term, that is linear in the nuclear spin and the electronic spin, and the coupling constant is usually such an A matrix. Then we have a nuclear Seemann term, and for this Mössbauer spectroscopy, in addition, we need terms to describe the so-called quadrupole interaction, which is an electrostatic interaction. This has to be solved because in Mössbauer spectroscopy, you will hear tomorrow that we have transitions between a nuclear ground state and a nuclear excited state. So we have to solve the spin Hamiltonian for the ground state and for the excited state. That would be a little bit tedious work when we would have now to increase also the basis function, because we would have now to form a product basis between nuclear spin and electronic spin. That makes the Hamilton matrix very large. But luckily, in this case, one can show if we apply a field of only 10 Gauss, which is a little bit more than Earth's magnetic field, then the energy separation of the energies of the Seemann energy of the electron is much larger than the hyperfine coupling. And in this situation, we can separate the problem. We can calculate the electronic properties first, and then derive something, then derive from that the spin expectation value. And we can replace in this operator, in this hyperfine coupling operator, we can replace the S operator by its expectation value. We solve the electronic part of the Hamiltonian, we solve the nuclear part, independent, and do not have mixing between those. That is true as long as we have fields of 100 Gauss or so. I mean, formally it would be 10 Gauss already sufficient. Let's say 100 Gauss we usually apply so that we have separated electronic spin and nuclear spin. In the physical manner, you could say, in this case, these two spins are processing around the field independent. If you have very, very weak field, the spin would couple and they process around the field together. And in this applied field situation, the two spins behave in their magnetic field independently. So that makes life numerically easy. So the Mössbauer simulation programs are pretty fast because we can replace the S operator by the expectation value, as I said. And then Mössbauer people usually define, or one can define, an internal field at the nucleus. Since we replace this hyperfine term, this hyperfine Hamiltonian, by the spin expectation value, we can call the spin expectation value times the coupling constant divided by nuclear G factor and nuclear magneton. In order to get this into a dimension of a field, we can call this the internal field at the nucleus. And the electron, the open shell, the spin of the electrons in the shell produce a field at the nucleus. And the effective field for this nucleus, or the field what it sees then, is the vector sum of the applied field and this internal field. And this internal field has now to be calculated for every electronic level. Each of these MS levels, or of these spin levels, has a different spin expectation value, and therefore a different internal field. So the Mössbauer spectrum, even for a single field direction, in a single crystal experiment, would be already the sum, the Boltzmann-weighted sum of these 6 contributions for a spin of 5½ So in general, then the procedure for calculating a powder Mössbauer spectrum would again be adopting a field and an orientation, one orientation, solve the electronic Hamiltonian, find the spin expectation values for these 2s plus 1 levels, and for each of these levels one has to calculate the internal field, make the vector sum with the Boltzmann weight factor, solve then the nuclear Hamiltonian, calculate the Mössbauer spectrum and sum it up with this Boltzmann factor, and this has to be done for all nuclear transitions, finding these transitions, these Mössbauer lines, and then one has to loop over the electronic levels and loop over the directions. So that's the way how to simulate a magnetic Mössbauer spectrum. Okay. So what else can we learn from the spin Hamiltonian? When it comes to magnetic properties, I have here now an example of a spin s equal 2. And let's assume we have a large negative zero field splitting. A single ion with a large negative zero field splitting iron 2, for instance. Then we know already from what we discussed before, without applied magnetic field, we will have a splitting in plus minus 2, plus minus 1, and 0. Because this is m to the square dependent. So these remain degenerate, these and these. And the zero field splitting parameter between these three, when we put in the m values, you can see this must be 3D, and this splitting must be 1D. So this is fairly well isolated when the D is correspondingly large. The Hamilton matrix, in the way we constructed it so far, would be this one. And this way to present the Hamilton matrix is a little bit inconvenient for what we want to consider now. Namely, how should be the behavior of these plus minus 2 magnetic levels, for instance? So we rearrange the Hamilton matrix. We can rearrange the Hamilton matrix in such a manner that we write it now in this sequence plus 2, minus 2, plus 1, minus 1, and 0 for the m quantum numbers, for the m functions. And what we see now is, or what we can easier see, is when this D is very large, and we have only a relatively weak applied field, for instance, in the x or in the y direction, then we would have an off-diagonal element which can mix the plus 2 and the plus 1, but that mixing will only be significant if the field would be very large, but that is not so easily possible if the D value is large. If the zero field splitting is let's say, 50 wave numbers or 80 wave numbers, which may be possible, for instance, for a cobalt complex or so, then, or iron 2 also under some conditions, in order to have an example with S equal 2, then it will be very difficult to change the nature of this plus minus 2 levels, because this off-diagonal matrix elements are small, given that the rhombicity parameter is small. So we need an axial system, and we generate something which has almost pure MS2 behavior for the ground state levels. And this argument that I'm constructing now, that directs towards the properties, the anisotropy of such a spin system. That the target is, let's say, how can we make a molecular magnet? And that would mean we need something which is magnetically very anisotropic and shows such an anisotropic behavior. For completeness, I can tell you that for up to s equal 2, I think there are closed shell solutions. I think for higher s, there is no closed shell solution anymore for the spin Hamiltonian without the Seemann interaction. I'm not aware of something. But for s equal 2, one can write the eigenvalues and the eigenfunctions still in closed form, provided there is no field applied. But what is more interesting to look at is now the magnetic behavior of this system. And you see, when we have this situation, rhombicity 0, and a d value of only -5 in our example, and we change the field up to 10 Tesla, we have here in the weak field condition, or in any of these conditions, we have large spin expectation values. These are now the spin expectation values, these are the energies. We have large spin expectation values of plus and -2 for the lowest Kramer doublet. And when we apply now a field perpendicular to this system, there is no magnetic splitting in the lowest Kramer doublet, so the nature of the wave functions does not change as long as we do not change the field larger to larger than 4 Tesla. And now the spin expectation values of this violet and yellow curve here, they are pretty small, so there is not much spin induced. And that means now, if we have such a system and we prepare it with a field in a z direction, make it magnetic in this case, and we now switch off the magnetic field, these are almost pure spin functions. So that would be very difficult for this system in order to change back into non-magnetic state in a thermal equilibrium where the whole system is non-magnetic. And so therefore, such type of systems are candidates for molecular magnets. And one can discuss that, one can derive them from the properties of the spin Hamiltonian. You see, when we switch on a rhombicity parameter in this case, we have for the spin expectation values, we have relatively easy change of these values when the fields are larger, when fields in the x or in the y direction are larger, the spin expectation values increase much faster, and then the nature of these wave functions is more complicated, and there are much more possibilities to relax back into such a situation. Okay, now I have the problem that I'm too fast. I'm at the end of what I have prepared for you, what I wanted to tell you. I would like to ask whether there are questions to this topic. Something about the Spin Hamiltonian Formalism, this generation of matrix elements. Was that clear to everybody? Okay, it seems to be the case, so then I close for now. Thank you for your attention.